Woohoo! It's a great day to be in geometry. This is Miss Legg-Battles, and I'm here to talk to you about a special type of right triangle, and first of all, the 45-45-90 right triangle. If you'll notice in our first case here, we have a right triangle that has a 45-degree angle and a right angle. Now, by the triangle angle sum theorem, that leaves 45 for the remaining angle. So this is one way that we could illustrate a 45-45-90 if we just knew one right angle and one 45-degree angle. Another way here on the right is if we have the two legs marked congruent. This is an isosceles right triangle. Isosceles right triangles are also known as 45-45-90s because remember from the isosceles triangle theorem that if two sides of a triangle are congruent, then the angles opposite them are congruent as well. So these would have to be 45 degrees each. Now, today we're going to talk about the ratios of the side lengths because, after all, every 45-45-90 triangle is similar to every other 45-45-90 triangle in the whole universe. They're all similar by angle-angle similarity postulate. So we're going to derive those ratios today. I'm going to let this length be x for the one leg, and I'm going to use the same thing for the other. Since they're congruent, I'm going to use the same variable. Now, I want to know the length of the hypotenuse with respect to x, so I'm going to call it c. We commonly let the hypotenuse be c because of the Pythagorean theorem, and in fact, that's what we're going to use here. Applying the Pythagorean theorem, I get c squared, which is the hypotenuse, the length of the hypotenuse squared, is equal to x squared plus x squared, the sum of the squares of the lengths of the legs. Now this will simplify because we can combine x squared plus x squared to get 2x squared, and then furthermore we can take the square root. Now we're going to ignore that this would be plus or minus the square root because we're finding c, and that's the length of the side of a triangle. So we're just ignoring the negative, and we'll end up with c equals the square root of 2 times the square root of x squared. Well, the square root of 2 won't reduce, but the square root of x squared would give us x, so I'm left with x on the square root of 2. So c would be x on the square root of 2. So I'm going to erase the c, and in its place put in x on the square root of 2. So this tells me the ratios in a 45-45-90 triangle. The legs are always congruent. They have the same length. So if this leg is 5, this leg is 5. The hypotenuse is square root of 2 times as long as the leg. So back to my example, if this is 5, this one's 5, and this one would be 5 on the square root of 2. If one leg is 20, the other leg is 20, and the hypotenuse is 20 on the square root of 2. Now, if we're going in the reverse order, if we know the hypotenuse and we're looking for the leg, we would have to divide by the square root of 2. So, of course, those are inverse operations. If you know the leg and you're looking for the hypotenuse, you multiply by square root of 2. If you know the hypotenuse and you're looking for the leg, you divide by square root of 2. Now, let's look at our theorem written in words. This is the way it's written in our text. The 45-45-90 triangle theorem states that in a 45-45-90 triangle, both legs are congruent. So I'm going to mark both legs congruent in this, my 45-45-90. Now, if you're drawing these, you might want to use the half a square on your template. Just use the square and do half of it, and then draw in your diameter of the square or the diagonal of the square, and that will give you a 45-45-90. And then it says that the length of the hypotenuse will be square root of 2 times the length of the legs. So if the legs are both x, then the hypotenuse would be x times the square root of 2, just like we had on the previous page. Now I'd like for us to look at some examples. So I've laid out 3 examples for us to look at today. The first one, the length of a leg is given, and we're looking for the length of the other leg and the length of the hypotenuse. And of course this is a 45, 45, 90 because we have a right angle, a 45-degree angle, and the one remaining would have to be 45 degrees. Number 2 is an isosceles right. 2 congruent sides, so that means these base angles have to each be 45. And then on the last one, both of the legs are labeled X, which means they have to be the same length. So it's another way of labeling it isosceles right. So this would have to also be a 45, 45, 90 triangle. Now, on my number 1 example, if one leg is 3, the other leg is also going to be 3. The legs are always congruent in a 45, 45, 90. And the hypotenuse is square root of 2 times as long as the leg. So that's going to be 3 on the square root of 2. In my second example, I'm given the hypotenuse and I'm looking for the leg. So to get the leg, I have to take the hypotenuse and divide by the square root of 2. So if I take 6 on the square root of 2 and divide by the square root of 2, the square root of 2's divide out, and I'm left with just x equals 6. Now, y is the other leg. It's going to be congruent to the previous one. So y will be 6 also. So let's review what we have here. On number 1, one leg was 3, so the other one is 3, and the hypotenuse is 3 on the square root of 2. On this one, the legs turned out to be 6. We have 6, 6, 6 on the square root of 2. Now, my third example, what happens if this is not a value times the square root of 2? Like on number 3, the hypotenuse is 8. Now, we still work it the same way. If you know the hypotenuse and you're looking for the leg, you're going to have to take the hypotenuse and divide by square root of 2. The problem here is that we have a radical in the denominator. So we have to get rid of it. And we can get rid of it through a process known as rationalizing. We're going to rationalize. Now when we rationalize, this is just going to get the radical out of the denominator. And it doesn't change the value of the problem. Square root of 2 over square root of 2 is just the same as 1. So we're multiplying by something equivalent to 1, but it's going to give me the same answer in a different form that no longer has a radical in the denominator. So I have 8 times the square root of 2 divided by square root of 2 times square root of 2, which is just 2. So that's what got the radical out of the denominator. So I end up with x equals, we can simplify here because these have common factors of 2. 2 goes into 2 one time, 2 goes into 8 4 times. So I end up with 4 times the square root of 2. And of course that's my only variable on this one because both legs turn out to be the same. They're 4 on the square root of 2. So this time I have 4 on the square root of 2, 4 on the square root of 2, and 8. You know, you could check this. We can check it by taking that leg length, 4 on the square root of 2, and multiplying it by square root of 2 to see if we get the hypotenuse. So square root of 2 times square root of 2 is 2, and 4 times 2 is 8. So yes, we do get the value of the hypotenuse, and it checks. I know you're going to do great on these, and 45, 45, 90 triangles are going to help you so much in your future mathematics. Have a great day.